In this session, we are going to introduce more complex NLP models. They are recurrent neural networks and Lstm network, two advanced deep learning models specifically designed for NLP tasks. A recurrent neural network is a type of artificial neural network which uses sequential data or time series data. These deep learning algorithms are commonly used for ordinal or temporal problems, such as language translation, natural language processing, speech recognition, and image captioning. They are incorporated into popular applications such as Siri, voice search, and Google Translate. Like forward and convolutional neural networks, recurrent neural networks utilize training data to learn. They are distinguished by their memory as they take information from prior input to influence the current input and output. While traditional deep neural networks assume that input and output are independent of each other, the output of recurrent neural network depend on the prior elements within the sequence. While future events would also be helpful in determining the output of a given sequence, unidirectional recurrent neural network cannot account for this event in their predictions. The visual above shows the working principle of a recurrent neural network. Suppose our input is a sentence, and each word in the sentence will be fed into the RNN model and produce a corresponding output, such as a machine translation task. At a particular time step t, it takes the word in the sentence as input, and it also takes the activation output from the time step t-1 as input. Therefore, recurrent neural network can give consideration to the context information in a sentence. Another distinguishing characteristics of recurrent neural network is that they share parameters across each layer of the network. While feed-forward networks have different weights across each node, recurrent neural networks share the same weight parameters within each layer of the network. That said, these weights are still adjusted throughout the process of backpropagations and gradient descent to facilitate deep learning. Recurrent neural network leverage backpropagation through time algorithm to determine the gradients, which is slightly different from the traditional backpropagation as it is specific to sequence data. The principle of BPTT are the same as traditional backpropagation, where the model trains itself by calculating errors from its output layers to its input layer. These calculations allow us to adjust and feed the parameters of the model appropriately. BPTT differs from the traditional approach in that BPTT sums errors at each time step, whereas feed-forward networks do not need to sum errors as they don't share parameters across each layer. As a popular deep learning model, recurrent neural network can be applied to multiple natural language processing tasks, and therefore, there are various forms of recurrent neural network, such as many-to-one, one-to-many, and many-to-many. Many-to-one architecture of the RNN is generally used as a common example for model of sentiment analysis or text classification. This type of model is used, as the name implies, where multiple inputs are needed to provide just one output. For example, we use the model for analyzing Twitter sentiments. A text entry is that model gives its set feelings. Another example may be the model of movie ratings. It uses review text as input to rate a movie that can range from 1 to 5. One-to-many sequence problems are sequence problems where the input data has one time step, and the output contains a vector of multiple values on multiple time steps. Thus, we have a single input and a sequence of outputs. One typical example is image captioning, where the model takes an image as input and produces a summary text describing the content of the photo. Many-to-many architectures takes multiple inputs and offer multiple outputs. but many-to-many models can be two types as shown above. When the number of input equals to the number of outputs, that is the position where it applies to the case where layers of input and output are of the same thickness. It can also be interpreted that as any output information can be found in named entity recognitions. Many-to-many architecture can also be represented in models where input and output layers are of different sizes. And machine translation demonstrates the most common application of this type of RNN architecture. As a consequence, machine translation models are able to return words more or less than the input stream due to the non-equivalent number of many-to-many RNN architecture that operates in the context. Although RNN used to be a very popular architecture for natural language processing, it has certain limitations itself. For example, RNN architectures stated above are capable of capturing the dependencies in only one direction of language. Basically, in case of natural language processing, it assumes that the word coming after has no effect on the meaning of the word coming before. With our experience of languages, we know that it is certainly not true. Secondly, RNN are also not very good in capturing long-term dependencies, and the problem of vanishing gradient emerges in RNN. The motivation behind why they happen is that it is hard to capture long-haul conditions as a result of the multiplicative angle that can be dramatically diminishing or expanding regarding the number of layers. So, if at all the sequence gets too long, the model may train with null weights or exploding weights. Another problem when it comes to parallelizing the training in RNN or a simple stack up of training is due to the fundamental characteristics of RNN. That is, they are connected. What this means is RNN requires the output of the previous layer to do the computation in the current layer. Due to this connection, RNNs are not suitable for parallelizing or stacking up with other models. The overall computational expense that goes on can never be justified with any accuracy gain. Therefore, these limitations give rise to new types of RNN architectures, such as long short-term memory model. Long short-term memory networks are a special type of recurrent neural network capable of learning order dependence in sequence prediction problems. Remembering information for a long period of time is practically their default behavior. In standard RNNs, this repeating module will have a very simple structure, such as a single hyperbolic tangent layer. Lstm also have this chain-like structure, but the repeating module has a different structure. There are 4 interacting natural neural network layers in a very special way. At a high level, Lstm works very much like an RNN cell. Here is the internal functioning of the Lstm network. The Lstm consists of 3 parts, as shown in the image, and each part performs an individual function. The first part chooses whether the information coming from the previous timestamp is to be remembered or is irrelevant and can be forgotten. In the second part, the cell tries to learn new information from the input to the cell. At last, in the third part, the cell passes the updated information from the current timestamp to the next timestamp. The key to Lstm is the cell states, the horizontal line running through the diagram. Lstm has the ability to add or remove information to the cell states, controlled by gates. Gates are composed out of a sigmoid neural network layer and a multiplication operation. I hope you still remember the sigmoid layer output number is between 0 to 1, describing how much information should go through. 0 means nothing can go through, while 1 means everything goes through. There are mainly 3 gates in an Lstm cell. The first part is forget gate. Second part is input gate, and the last one is the output gate. just like a simple RNN. And Lstm also has a hidden state, where ht-1 represents the hidden state of the previous timestamp, and ht is the hidden state of the current timestamp. In addition to that, Lstm also have a cell state represented by ct-1 and ct for previous and current timestamp respectively. Here, the hidden state is known as short-term memory, and the cell state is known as long-term memory. It is interesting to know that the cell state carries the information along with all the timestamps. The first step in an Lstm cell is to decide how much information we will throw away from the previous cell states. And the equation for forget gate is shown here. It takes the hidden state output from the previous timestamp and input at the current timestamp as input, and use sigmoid function to transform the input to an output number between 0 to 1. If output is 0, then the network will forget everything. And if the value of output is 1, it will remember everything. The second step is to decide what information we will store in the cell states. And this is exactly what the input gate is doing. Input gate is used to quantify the importance of the new information carried by the input. Here is the equation of the input gate. It takes the hidden state output from last timestamp and input at the current timestamp as input, and transform using sigmoid layer. Now the new information that needed to be passed to the cell state is a function of a hidden state at the previous timestamp t-1 and input x at timestamp t. The activation function here is hyperbolic tangent function. Due to the hyperbolic tangent function, the value of the new information will be between -1 and 1. If the value is ct wave is negative, the information is subtracted from the time state, and if the value is positive, the information is added to the cell state at the current timestamp. The third step is to update the old cell state ct-1 to the new cell state ct. We'll multiply the old cell state by ft in order to forget the information we decided earlier at forget gate. We also multiply the new candidate ct wave by it in order to update the information we decided earlier from input gate. The final step is to decide the final hidden state output ht. Here is the equation of the output gate, which is pretty similar to the two previous gates. Firstly, we'll run a sigmoid layer to decide what parts of information we are going to output. The value of OT will also lie between 0 and 1 because of the sigmoid function. Now to calculate the current hidden state, we will use OT and hyperbolic tangent function of the update cell state CT. It turns out that the hidden state is a function of long-term memory CT and the current output. If you need to take the output of the current timestamp, just apply the softmax activation on hidden state HT. Here shows the more intuitive diagram of Lstm network. In conclusion, Lstm network is an advanced version of RNN with the combination of forget gate, input gates, and output gates. Lstm network is able to learn long-term dependencies for natural language. Later on, the idea of bidirectional Lstm was introduced, which can overcome the limitation of regular RNN, while the model is trained using all available input both in the past and future. Lstm networks are well suited to classifying, processing, and making predictions based on time series data, since there can be a lack of unknown durations between important events in the time series. Lstms were developed to deal with the vanishing gradient problem that can be encountered when training traditional RNNs. Relative sensitivity to gap length is an advantage of Lstm over RNNs, hidden Markov models, and other sequence learning methods in numerous applications.